In this problem, we're going to be analyzing a pumpkin sliding down a hill and hitting a spring. We're supposed to figure out how much the spring gets compressed. First thing we want to do is lay out the steps that we're going to use to solve this problem. First step would be to draw in the h equals 0 line. That's our gravitational potential energy reference height. Next thing is we'll pick the initial state, and we're going to pick the initial state as when the pumpkin is at the top of the hill. It's 3 meters higher than the spring, and the spring is not compressed. The final state is going to be when the pumpkin is at rest, sitting against the spring. So velocity is 0, height is 0, and the spring is compressed. Then we're going to draw a free body diagram and identify the non-conservative forces. Draw a work diagram for each non-conservative force. Write out and I should back up. The reason we're doing steps 4 and 5 is so we can figure out if there's any work done by non-conservative forces, and if there is, quantify it. Step 6, write out the conservation of mechanical energy equation, cross out terms that are 0. Finally, solve for the unknown, which in this case is x. Alright, let's solve for let's go ahead and start these steps. Oops. So we've got our h equals 0 line drawn in, that dashed line right there. So I'll go ahead and label it h equals 0, and the other way to label it is to say that gravitational potential energy is equal to 0. Alright, and we can go ahead and label our states up here. This is initial. We don't have to call it state A anymore. So hi equals 3 meters, vi equals 0, and delta xi equals 0. Down here, we're going to have our pumpkin sitting here, and that's going to be our final state. And we're going to say hf equals 0, vf equals 0, and delta xf equals, well, we don't know. Alright, so now we'll finish this step, this step, this step. Alright, free body diagram. Well, we can go ahead and do that on the next slide. We're actually going to have 3 free body diagrams. So there's one where it's on the hill. We've got normal force and weight, but this is perpendicular. The normal force is perpendicular to the displacement. Same thing when it's on the horizontal part. The normal force is perpendicular to the displacement. And then we've got the final part where it's still on the horizontal, but we've got the spring force acting. So spring and weight are conservative forces, so normal force is the only non-conservative force that acts at any time between initial and final, and so the work by non-conservative forces is 0. Okay, so we'll just make a note here, a different color. We'll just say always perpendicular to the displacement. So that's how we know that the work by non-conservative forces is equal to 0. Alright, so we're talking about Chapter 7, conservation of mechanical energy. We don't need a coordinate system since we're not summing forces. We don't have any reason to have a coordinate system. We are trying to find delta x. It should have a positive value, and it should have units of meters. Alright, so we're going to use this conservation of mechanical energy equation based on our diagram on the last slide. We know that the velocity initial and final are 0, so we can go ahead and get rid of the kinetic energy, initial and final. We also know that initially there's no spring energy. We can get rid of that. We just talked about how there's no work by non-conservative forces, and when it's in the final state, the height is 0, so there's no gravitational potential energy. So this is going to simplify things greatly, and we're going to go ahead on to our executing our plan. So we have mghi equals 1/2 k delta x f squared. Now we can plug in values, solve for the unknown. So we could start off by dividing both sides by k, and multiply both sides by 2. So then we get 2 mghi over k equals delta xf squared. And then we can take the square root of both sides. And so delta xf equals square root 2 times 10 kilograms times a height of 3 meters. Oh, and I'm doing it in a different order. Forgot my g there. Acceleration due to gravity, 9.8. And then divided by k, which is 2,250 newtons per meter. All right, now we go ahead and plug this in. Delta x. And so grab the calculator, check on this, make sure I'm doing this right. 2 times 10 times 3 times 9.8 divided by 2250. Take the square root of that whole thing. Get 0.511 meters. All right, and that is what the answer is up there as well. But make sure you're able to do this calculation. Let's also look at the units. We've got kilograms, meters, meters per second squared. In the denominator, we have newtons per meter. So I'm going to put it as newtons, and then I'm going to flip the meters up into the numerator. So this is quite a mess. We also have the square root of that. So does that really equal meters? It sure is hard to tell. So let's take a closer look. The thing that we could do here would be to let's just leave those separate, and then we'll take the Newton and we'll split it into kilogram meter per second squared. And since that's in the denominator, we can put the second squared up there. So the only thing different between these two lines is I took the Newton, made it into a kilogram meter per second squared, put that in the numerator. So now we get kilogram meter, second squared cancels with second squared. We're left with the square root of meter squared, and the square root of meter squared is a meter. So the units do work out. The sign is correct. We did solve for everything we were supposed to. And is the magnitude of the answer reasonable? Really quite hard to say in this case. All right, let's look at our initial energy compared to our final energy, include the work. Actually, the work is 0. So we started off with some amount of gravitational potential energy. We'll say that was 4 bars worth, and we ended up with that exact same amount of spring potential energy, 4 bars worth, and that's it. Very simple in terms of our energy bar chart.